Good morning, guys. All right, here we are. We're going to start with this. You solve, I'll meet you in a minute. Pause the video, go. We're starting on the very, very inside, so I'm going to set this stuff equal to theta. I know tangent inverse 3/4 equals something, so I'm going to call that something theta. So I have tangent inverse of 3/4 equals theta. Hit both sides with tangent, and I'm going to flip it around just because that's better for my brain. With tangent, we know that's TOA, and we also know that a positive 3/4 could be a negative 3 over negative 4. So I'm going to set up my triangle. Got a positive 3, a positive 4. I could also have a negative 3 and a negative 4. So I have two triangles like that. And if we're trying to solve the inverse, we know that we're going to have one and only one answer. Which one is it going to be? Which angle wins? Is it this guy here or this bigger guy down here? And it's this smaller guy right here. So we know this is the angle that we're dealing with. This is the tangent inverse of 3/4. And now we need to find the cosecant of it. Cosecant is CHO, that's hypotenuse, over opposite. Our hypotenuse is 5. You could use the Pythagorean theorem, or if you just know a 3, 4, 5 triangle. Either way, CHO, hypotenuse, over opposite. We know this all equals 5/3. Now, slightly different question. What if the question had just been tangent inverse of 3/4? It plays out the same. We know that we have two different angles. We know we have this one here and this one here. We know that this one wins, but then what is this angle actually equal to? We don't know. I mean, our job at this point is to just give a calculator-ready equation, or if you have a calculator, you would go ahead and plug it in. But this is the angle we're dealing with. We don't know what it is. We just know that it equals theta, and this right here is a calculator-ready equation. If this was the only question we were being asked, hey, what's tangent inverse of 3/4? Tangent inverse 3/4 equals theta. It's calculator-ready. It's ready to go. That's the best we can do at this point. So now moving on. We're going to look at a problem that looks like something that we're good to go on. Secant squared x minus 2 tangent x equals 4. But it's going to end a fair bit differently. Now, again, you can do most of this. So you work, I'll meet you in a minute, pause the video, come back when you have it down to isolated trig functions. So get going. I can't deal with secant and tangent in the same equation because I can't isolate either one. And so I'm going to use my Pythagorean identities, secant squared x minus tangent squared x equals 1, and I'll be able to solve secant squared x equals 1 plus tangent squared x. I'll plug this in for secant squared x. I have 1 plus tangent squared x minus 2 tangent x equals 4. I'm going to get everything on one side. So I have tangent squared x minus 2 tangent x minus 3 equals 0. Now, if the tangent was a plain old variable like x squared minus 2x minus 3, I'd be thinking that I have to factor, and it's the same when it's not just a plain old variable. It's the same when it's a trig function. So I'm going to factor using tangent instead of plain old x. So I get tangent x minus 3 times tangent x plus 1 equals 0, and it's worth it to take like 2 seconds, multiply through, make sure that you factored properly. And I did. So now I'm going to set this guy equal to 0, set this guy equal to 0. We get tangent x minus 3 equals 0, and tangent x plus 1 equals 0. So now isolating each trig function, we get tangent x equals 3 and tangent x equals negative 1. It still looks pretty normal, and the right side is going to play out completely normally. So let's go ahead and finish that side off. We get tangent x equals negative 1 over 1 or 1 over negative 1. Tangent is SOHCAHTOA TOA. So when I look at this, I have an opposite of negative 1, an adjacent of positive 1. That makes a 1, 1 square root of 2. Or we have an opposite of positive 1 with an adjacent of negative 1. That makes a 1, 1 square root of 2. And at this point, this is the angle setup that we have. We know this is a 135 or a 3 pi over 4. And if this was all that we were dealing with, if this side was the only side we had, we would have 3 pi over 4 plus a straight line pi n. But we do have to look at the left side also. So coming back to the left side, we have tangent x equals 3. That's 3 over 1. And of course, it could be negative 3 over negative 1 also. So I'm going to set that up. I have an opposite and an adjacent, an opposite of positive 3, an adjacent of 1, an opposite of negative 3, an adjacent of negative 1. These are the two angles that we're dealing with, but they aren't common angles. They aren't the 1, 1 squared to 2, 45, 45, 90 that we know. They aren't the 1, 2 squared to 3, 30, 60, 90 that we know. It's a 1, 3 something. I could figure out the third side using the Pythagorean theorem, but that's not the question. The question is, hey, what solves this equation? What angle can we put in to make this equation work? So they're looking for angles. They want to know what angle this is right here. There's nothing that would cause us to disregard the entire left side of the equation, and so this angle is the answer, and what we have to deal with is tangent x equals 3. So what solves for x? What is x? We would apply a tangent inverse to both sides, and we would have x equals tangent inverse of 3. That's what the angle is. I can't tell you the exact number unless I grab my calculator, and I don't need to do that. I just need to leave it as a calculator-ready equation. We have x equals tangent inverse of 3. Now, at this point of the problem, we would usually consider both of these answer sets on the same graph to see if they were evenly spaced all the way around. They're not going to be evenly spaced all the way around because on the left we've got some kind of random unknown angle, and on the right we have normal 45, 45, 90 triangles going on. So we don't have to put them on the same graph to compare the spacing in between them. What we do need to do is deal with each one separately. So I have x equals tangent inverse of 3. That's technically this angle here. And then it spins in little half circles. So we have tangent inverse of 3 plus pi n. And then as we talked about before, this is 3 pi over 4 plus, again, little half circles. So it's going to be plus pi n. And that's it. That's the answer that we're looking for. So let's try a different problem that also involves secant, but it'll play out a little bit differently at the end. Let's go with secant squared x plus 2 secant x minus 8 equals 0. Go ahead and pause the video, see how far you can get with this, see what you can come up with, and then come on back. So I'm going to go ahead and factor. I get secant x plus 4 times secant x minus 2 equals 0. Take a split second to factor or multiply it through to make sure it's right. And I'm good. So I'm going to set this guy equal to 0. I'm going to set this guy equal to 0. So I have secant x plus 4 equals 0. And I have secant x minus 2 equals 0. That gives me secant x equals negative 4. That gives me secant x equals 2. So again, I'm going to deal with the right-hand side first. Secant x equals 2 over 1. That's Cho-Sha. That's hypotenuse over adjacent. So I'm going to look at my axis. I'm going to find a hypotenuse of 2 with an adjacent of positive 1. A hypotenuse of 2 with an adjacent of positive 1. This is a nice normal 1, 2 square to 3, 1, 2 square to 3. It'll be negative in this case. And we know that this is a 60 and this is a 60. We'll switch to radians in a little bit, but let's see how the left side plays out. So I have secant x equals negative 4, which is negative 4 over 1. The negative is going to belong to the adjacent. I know secant is hypotenuse over adjacent. And so I'm going to look for all the places where my hypotenuse is 4, but my adjacent is negative 1. Hypotenuse of 4, my adjacent is negative 1. Now, can this triangle exist? Can you have a hypotenuse of 4 with an adjacent of negative 1? Yeah, sure you can. I don't know what the third side is, but that's okay. I don't really need to know what the third side is. The question is simply, what is this angle here? What is the angle that goes along with this triangle? So coming back to what we had secant x equals negative 4. Now here's the thing. These need to be put into calculator-ready form. And secant or secant inverse is not a button that we have on our calculator. So I'm going to go ahead and turn secant into cosine. Secant is 1 over cosine x. Multiply by cosine, divide by -4. That's going to give me cosine x equals 1 over -4. To get x all by itself, I'm going to apply a cosine inverse. And so I'm going to have x equals cosine inverse of -1/4. I need to flip that around just because it's more comfortable to write this way. And this is where I am. I have x equals cosine inverse of -1/4. Now this situation played out differently than the problem we had before. The problem we had before, let me take you back up there, our tangent inverse of -3 was this angle here, but it was back to back in a straight line with the other angle. Coming down here, we have two very different looks. We've got this angle here, and we have the lower angle, the negative version there. Which one is the actual cosine inverse of -1/4? Cosine inverse, remember, can only have one correct answer, and you're going to pick the one with the smallest absolute value, and if there's a tie, you're going to go with the positive one. Cosine inverse of -1/4, technically speaking, is this angle up here. And so dealing with that angle, our first answer is cosine inverse -1/4, and then it spins in full circles. So it's cosine inverse -1/4 plus 2 pi n. Now the other angle, remember with inverses you can never go past 180. So I can't tell you what this angle is, this green one that I'm drawing in. I can't tell you what that is. We don't go past 180. Instead, I'm going to be dealing with this lower angle here. And if the top angle is a positive cosine inverse -1/4, this lower angle is going to be a negative cosine inverse -1/4. We have two possible answers. They both work. They both solve the equation. The first one is positive cosine inverse -1/4, and then full spins around the circle. The next one is a negative cosine inverse -1/4, and it also has full spins around the circle. Now back on the right side, remember we had our little 60-degree and 300-degree answers, and so converting both of those to radians, and both of them are going to spin in full circles around the axis, we have pi over 3 plus 2 pi n, and we have 5 pi over 3 plus 2 pi n. Now we chose to go with 300 instead of -60 because traditionally speaking, we always want to keep our answers positive for this type of problem. But that causes us a small problem with this answer that we had right here. We have a negative cosine inverse -1/4. That was this pink angle that we're dealing with on the left side. Well, first of all, I personally don't care. If you want to give me a negative cosine inverse -1/4 plus 2 pi n, I don't have a problem with that. The keep things positive is a tradition more than a hard and fast rule. And when we're talking about infinite spins around the circle, it really doesn't matter if we start with a negative angle or a positive angle. But some people do care. And so you might see very different versions of this answer. Consider a situation where I had a -90 as an answer, but I wanted my answer to be equivalent but positive. In other words, I wanted a coterminal angle. I could add 360 and get 270. 270 would also be an answer. And that's the basic concept of what some people might do. They would take the negative cosine inverse of -1/4, and then they would add 360. And then they would spin in full circles. And this right here with the plus 360 is a positive angle, and they spin in full circles off of it. And then again, to make things a little more interesting, sometimes they switch it just so it reads more like subtraction. 2 pi minus cosine inverse of -1/4 plus 2 pi n. Again, I don't care if you give me the more basic negative version, but if you see these other more interesting versions, they're just coterminal answers that come from the basic answer. We'll practice this a little more in just a bit.